Okay, welcome to Tuesday. We are going to be doing lesson 5, but before we do that, please open up your textbooks to last night's homework. I want to go over a few of these. We're on page 579, and the first two I want to look at is 3 and 4. So now is your chance to make corrections and changes if you didn't do this correctly. So it says find the length of each model, then find the scale factor. So we first start with our scale. 0.5 centimeters is to 1.5 meters equals, and if you weren't sure if this 36 meters, if this was the scale or the actual, a big clue is the units. Since it's meters, it has to go on the denominator so that the units are the same. So we set this up and then we cross multiply. So 36 times a half is 18. Equals 1.5x. Then when we divide by 1.5, x comes out to be 12 centimeters. So that's how tall the model would be of this Ferris wheel. But the second part says find the scale factor. So what you need to do now is start back with your scale. And to go from a scale to a scale factor, we need to get it so that our units will cancel. Well, the first thing I want to do is I want to get rid of this 0.5. I don't want to deal with decimals. So if I multiply this by, let's say if I move the decimal one place, is this the same thing? 5 centimeters is to 15 meters. Okay, do you agree with that? So now we need to figure out 1 centimeter, or it takes how many centimeters to fit into a meter? Aren't there 100 centimeters in 1 meter? So if we have 15 meters, isn't that going to be 1,500 centimeters? So 5 centimeters over 1,500 centimeters, then we divide both of these by 5. 5 divided by 5 is 1. 1,500 divided by 5 is 300, and then we can cross that out. So our scale factor is 1 to 300. That means our scale is 300 times smaller than the actual. Okay, so for the airplane, 2 inches is to 15 feet. So we do x over 87 feet. When you cross multiply, you get 174 equals 15x. Then you divide both sides by 15 to get x equals 11.6 inches. Okay. So now we want to turn this into our scale factor. So we do 2 inches is to 15 feet. So there are 12 inches in a foot, so 12 times 15 is 180 inches. And then we can reduce this. 2 divided by 2 is 1. 180 divided by 2 is 90. So we have 1/90. Okay, turn the page please. In this problem of New Mexico, 1 centimeter is to 25 kilometers. So then to find the distance from Eunice to Hobbs, when we put our ruler here, notice that it's a little bit hard to see, but 1 centimeter is right here. Do you see it goes 2 tenths above that? So this is 1.2 centimeters away. So we need to find the actual distance. So we do 25 times 1.2. It comes out to be 30 kilometers. Okay, so if you need to go back and revisit or change any of these, please do that. Let's go down to 15. A model of a tree is made using a scale of 1 inch is to 25 feet. What's the height of the actual tree if the model is 4 3/8? Well, it never hurts to figure out, is 3/8 a terminating decimal? And it is. I just did 3 divided by 8 on my calculator and I got 0.375. So because it's a terminating decimal, we can change that. So now I'm going to cross product that. So 4.3 375 times 25 comes out to be 109, and I'm going to round it to the nearest tenth, 0.4 feet. Number 16, a map of Bakersfield has a scale of 1 inch is to 5 miles. If the city is 5.5 inches across the map, how many miles is that? When you cross products, you end up getting 26 miles. Okay. The next one says Tyson is creating a scale drawing of the area of his school. The rectangular drawings show the length of 20 inches and a width of 19. And the scale they're using is 1 inch is to 3 feet. What is the actual area of the school? So if 1 inch is to 3 feet, 20 inches is going to be 60 feet. And 19 inches is going to be 57 feet. And I figured that out just by doing the calculation. I just multiplied 20 times 3. So now the question is, what is the actual area? Well, the actual area is 60 feet length times 57 feet width, which comes out to be 3,420 square feet. Okay. Turn the page, please. And I'd like us to look at number 20. A carpenter sawed a piece of wood into 3 pieces. The ratio of the wood pieces are 1 to 3 to 6. Okay, so let's draw that. We've got 3 pieces, 1, 2, 3. To show a ratio of 1 to 3 to 6, we're going to do 1x, 3 x's, and 6 x's. Then it says the longest piece is 2.5 feet longer than the shortest piece. So if you look at your drawing, the difference between the longest and the shortest is only this amount. So this whole amount is 2.5 feet. Okay, so it says now we have to figure out the length of the original piece. Well, 1, 2, 3, 4, 5. If these 5 pieces are 2.5, notice that the remaining of our model, 1, 2, 3, 4, 5, there's another 5 right here. So 2.5 times 2 means we have 5 feet altogether. Okay, number 21. When you solve this to do cross products, you should have gotten 5b equals 50. So b comes out to be 10. The next one should be 147 equals 7a. So a is 21. And the next one, when you do cross products, 99 times 2 is 198 equals 9x. And when you divide by 9, x comes out to be 22. So that's a really good review for M-STEP, so make sure that you're catching on to those proportions. The last one I want to go over, Dante has 60 baseball cards. That means it's referring to these 60. So 60 baseball cards. This is at least 6 more than 3 times however many cards Anna has. So this 60 is at least so we're going to set up this portion. We're going to subtract 6 from both sides to get 54 is greater than or equal to 3a. Divide both sides by a. That means Anna has 18 or less cards. Okay. Please turn to where it says draw 3-dimensional figures for lesson 5. Okay, I'd like you to take just a minute to pause this, read through the real world link, and when you've had a minute to look at it, then restart. Okay. So if we were to stand and look at this building from the side, do you see that we would see flat from the side, we would see a rectangle. If we looked at it just from the top, we would see a triangle. Okay. All right, so from the side we would see a rectangle. From the top we would see a triangle, just like this. The top view, side view, and front view of a three-dimensional figure are shown below. Sketch the figure. Okay, so see if you can do that. So from the side, we are going to see 6. From the front, we're only going to see 2. And from the top, we're going to see 6. So from the side, looking this way, it's going to look like this. From the front, it's going to be as if we were standing right here looking this way. We would just see these 4. And from the top, it's like we were a bird looking straight down. We would see those. Okay, turn the page. Okay, you're going to have a little bit of time to draw three-dimensional figures from different views, so practicing top, front, and side view. So this first example, the side is always from the shape if you move just a little bit to the left. So if you stood and looked at this right at the side, you would just see this rectangle. So that's where our side view is. If we stepped around here and looked at it from the front, here, and the top view is always as if you were standing from the side and flew straight up from this side. So notice if you looked at it from this side, notice how we're seeing it in this direction. That's why it's tilted that direction. Okay, so once again, top, front, and side views here. I'll take a minute to draw the appropriate views here, and once you've got them drawn, hold the video or restart the video. Okay, so for this one, your side view, it's going to be here. Your front view, it's going to be longer. So we're looking at it right here. And your top view is always from the side up. Okay, so when we look at it from the top, it's going to be like this. Okay. All right. Please pause the video and do this, and have Mr. Sears initial this when you're done, that you've got those done. Okay, example 4. We're going to draw what's called a corner view using what's called isometric dot paper. And once you start using these dots, it's really a lot of fun. I would suggest that you make sure that you use a ruler, or I'm sorry, not a ruler, a pencil with an eraser, because you will make mistakes. But it's kind of just using some logic. Okay? So I don't like the way they did this, because they are doing the front and side different than the way we normally do in engineering. But notice that they are calling this the side view, and if we were to look at the side view, we would only see those 3 blocks. Okay, top view straight across and front view straight across. Okay, so let's try this one. Draw a corner view of the three-dimensional figure whose top, front, and side views are shown. Okay, so from the top we can see 4, but from the side we can only see 2 crossed, and the front we can only see 2 across. Okay, so we're going to go over here. And so from the side, I'm going to draw 2 lines on the diagonal. And then I'm going to go straight up 2. So from this side, I'm looking this way and I see 2. And from the front, I see 2. So front, side. And from the top looking down, I see 4. So these are all going to be filled in. Okay, turn the page. Okay, once again, please pause the video. Complete these 2 things and then restart the video to see the solutions. Okay, so my side view is going to be looking right here as a rectangle. My front view is looking right here. This one's a little bit different because when I see the front view, it's as if this were flattened out. I'm going to see this. I'm also going to see this and this. So my front view is going to look like this. Here's this edge. This face is right here. I'm going to see these little creases here, and I'm going to see those 2 flaps there and there. And my top view is going to look like this. Okay, so now your corner view of a top, front, and side here should look like this. All right, so if you look on the next page, your assignment will be given to you by Mr. Sears or will be put in your assignment guide, but you're going to work through these next couple pages.